Hello and welcome to Algorithms Live. This week I'm speaking with Scott Wu about his experience writing problems for Venture Cup. So we'll talk a lot about Venture Cup itself, some of the work he's been doing with streaming and competitive programming, and then we're going to talk about a problem from Venture Cup that I think is kind of cool. And I've posted that in the blog, so you can just follow that link, try solving it yourself, and then watch the explanation. Um, so Scott, thanks for coming on Algorithms Live.
Yeah, absolutely. Thanks for having me. I've done some streams before. We did an episode before. I was trying to do actually like some of the post-run streams for a while, but haven't gotten to do that too much lately. So it's good to be back.
Yeah, pretty cool. And let's look at some information on Scott. I remember the last episode we did, I think it was around this time last year,
Mhm.
but we had some technical difficulties or we were like rushing through the beginning and I didn't give you a proper introduction. So here's the better introduction to Scott. So he's the co-founder and CTO of Lunch Club. So that's a startup in San Francisco. He's doing that. I think you're doing that with a former competitive programmer as well.
Okay, another former IOI contestant. Yeah.
Ah, cool, cool. What country was he from?
He also competed for the US. Yeah, he got
Okay.
selected, I think, back in '01.
Okay, cool, cool. And you're also an ICPC World finalist. You got third place in 2016,
Hmm.
right? Right?
Yep. Yep. And so programming contests, math contests, all of that was basically my life up until I guess, start of college. And then that's kind of when I started branching out into other things. I really, really love programming contests, to be honest. And I still do it for fun sometimes. But yeah, now I work full time on my startup in San Francisco. So
Cool, cool. And then, of course, people remember you as the IOI champion in 2014. That was in Taiwan.
yep,
Pretty cool.
yep.
So,
Thanks.
yeah, yeah. So, I guess we can start moving the conversation into streaming. Like,
Mhm.
you were obviously on Algorithms Live last year, but then you also had been doing some Codeforces kind of like post rounds
Yep. Did the
discussions.
Codeforces post round? Yeah, I was commentating at Top Coder as well, Top Coder Open.
Oh
So
yeah,
that was
yeah. I think previous episode we were talking about TCO and then like the commentary.
Mhm.
Yeah, and so you were doing that with Lewin. Anyone else involved or?
Yeah, we brought on different guests kind of from the people that were on site, but it was mostly Lewin and I. And it was a really good experience, honestly. It was a lot of fun. I think people had a good time watching it. We got some good feedback as well. So
Yeah, yeah. I had a discussion with Arichto because he was one of your guests on the TCO.
yeah, he
Yeah,
came.
and we were talking. We did a episode on like just streaming in general, and we went into a conversation about like these broadcasts. You look at ICPC Live, obviously being the first like really big one, but then um, Top Coder Open, Google Code Jam, and all these different services. So I are all these different broadcasts. So what do you think made the TCO broadcast this year unique?
Even the individual streams. I mean, like you mentioned, Arita does a lot. Other people have been kind of starting their own kind of like commentary streams or educational streams. I think it's all really, really good. I think it's the kind of thing we need more of in the community. TCO was, the staff at TCO was super, super helpful, and they were able to give us everything that we needed. They gave us an iPad so that we could do drawings on the board. They gave us the problems and had all the setup and the analysis in advance. Kind of had everything that we needed to be able to make that into a fun and interactive experience. So that was really awesome. I think in general with streaming, I think there's a lot to go. I personally, I'll say I watch a lot of video game streams myself, and
Hmm.
it's really awesome what a lot of these players and participants do to make it interesting and to make it exciting. And I think we have a lot of that too, kind of like, or we have a lot of potential there too in the competitive programming community to do the same stuff. So.
Yeah, yeah. Well, I talked about this with Arichto. I think I'll bring it up with you. Like one of the main inspirations to Algorithms Live was I watched the TCO broadcast in I think 2016, and they didn't have expert competitive programmers on their broadcast. So you'd have like an interview with like Piotr or any of these top contestants, and they'd be asking like really basic questions about their background or day to day life, like in their day job or whatever. but they weren't really like the questions I'd want to ask like a competitive programmer. And
Right.
then it's also like you want to like see how they think, you want to see how they like process problems. Like you don't see a lot of that when you're competing. Like if you're just watching like a screencast of them competing. And so I think like if I compare 2016 like TCO with this year's TCO broadcast, it was like way more improved just because you and Lewin did a great job just covering the problems, talking about the problems, and talking with the contestants after. So I think it was definitely a big improvement. But I'm also kind of happy that the original stream wasn't that good because I realized, like, it basically one of the things that inspired me to do this stream.
Right.
And so I think it's kind of interesting, but I think it's also interesting, like, we have such a long way to go.
Yeah.
Uh,
Yeah.
what things would
It's
you
hard,
think?
right? Like,
What? Hmm?
yeah, I mean, it's really tough. Like, obviously, you also have to be you have to be a great competitive programmer to start. But there's a lot too about just kind of being able to teach and being able to explain these topics, being able to go into detail about the problems,
Hmm.
and to just kind of to flow with that. So I think we're all getting better, and it's great to see, yeah, the community kind of improving as a whole. And I totally agree, we have a long, long way to go. So.
Yeah. So what things specifically would you like to see in streams or even with like ICPC broadcasts or
Mhm.
TCO broadcasts?
Yeah. Honestly, so I think the kind of so you were saying, at the beginning, most of what we had was kind of the high level, like kind of I'll call it soft commentary, where it's just kind of like what's going on with the match, who's winning, maybe do a quick interview with the winner, ask them how they're feeling, and so on. Now we're doing more of the kind of the analysis commentary and really looking into the problems, getting into depth with the statements. I think that there's a lot of cool ways to mix those two together. If you think about in sports how they have kind of the play-by-play and then the color commentator and all of that.
Hmm.
Um, I would love to see that kind of mesh together, and I think that we can do better with that. So.
Do you think there are any tools that could be added that would make these kind of live broadcasts better, or tools you'd like as a commentator?
Yeah, that's a good question. So one thing that TCO had, which was a real luxury, I would say, is like the ability to watch the competitors' screens.
Hmm.
So we could see not just when they were submitting, but also what problems they were working on. We could even see them running their test cases or so on. And there were a lot of cool things that came out of that because, let's say Piotr submitted 500, but he wasn't so sure about it. And we could tell because he was still running tests, doing things on his own IDE, on
Hmm.
his machine. And we wouldn't have seen that from the outside. So I think more of that would be awesome. It is starting to become kind of a staple. I know ICPC has that too now.
Hmm.
So.
Yeah, I definitely. Well, I enjoy the screencasts and the broadcasts, so you can like pull up somebody's screen and then see it. I think personally for me, there's a feature when you go to ICPC World Finals, you can sit at these terminals and you can look at anyone's screencast.
Uh,
And they kind of get clogged because like a coach will grab it and they'll want to see their team. But I
yeah.
think having a feature like that where anyone
Okay.
could view anyone's screen during
Yeah.
like if you're let's say you were at TCO and you had like I think there's like 8 contestants in a round.
Yep.
Yeah,
Yeah.
just
And then you could kind of come on and watch any of those if you wanted to.
yeah, that would be really cool. I don't know how feasible that is. I don't know how they would do it, but that's something I would personally enjoy a lot of, like be able to hear the conversation in the background, but switch to their screen.
Yeah, kind
Another,
of to channels. Yeah. Yeah, I think that's really cool. And actually also just kind of thinking from the competitor side, I was going to say, it makes me wonder if that's a lot more kind of like nerve inducing, if you know what I mean? Just because it's like, now you know that your friends can watch you, all the way through from home instead of kind of just having these glimpses of a few seconds at a time. But yeah, honestly, I think that would be really good. And it's kind of, yeah, it definitely reminds me of kind of the ability to change channels.
yeah, I think another feature that would be really cool, but I don't know how easy it would be to do, but maybe a camera for each workstation. You could also like show if they're working something out on paper,
Mhm.
you can kind of
Oh,
see what they're trying to do because a
uh,
lot of times when you'll have these moments, and I noticed in the TCO stream, right? you're you're like, oh, let's go look at this contestant now, and then they're not doing anything on their monitor. It's like, oh, I think they're working on paper,
Yeah,
working through
we
something.
have to, yeah, right.
So
Yeah, I know exactly what you mean. Yeah, and that's really cool. Yeah, I think especially one thing I've been thinking about as well is like I think that there's more room for kind of like faster paced contests. You know, if you think about like the start of the Codeforces round or things like that, where people are kind of solving a problem every few minutes, the top contestants. Um, and then like in that kind of format, honestly, I think there's a lot kind of really interesting viewership stuff, and like I think the webcams is one of those things too, because you actually get to see these contestants moving at lightning speed, um, and like in real time. So totally agree on that one.
yeah, so I looking back to so I was helping with the Yusuko camp 1 year. I think this was after you were competing, but we did this thing called a lightning round,
Hmm.
and I think it was something like 30 problems. Um,
Yeah.
yeah, 30 problems. You had 2 hours, and what they
Uh,
were was they were just like classic problems. Every problem had the same input, so it was we had to cow theme everything. So every problem just started with the word moo.
uh,
And so it was like the lightning round was like we wrote like all 30 problems in 1 day. Um,
oh.
yeah, so it was like moo, you were given a tree, and then like all the problems had the same input. So it was like you were given a tree, and then
Uh,
there was a type of problem. It was like you were given a tree and then some queries on the tree. So like pairs of vertices, or you
yeah.
were given a sequence, or you were given a sequence with some queries on the sequence. And there's a lot of problems even with just that input format uh, that are they're interesting. Like, but
I
we
bet.
yeah, we ended up doing a lot of like classic algorithms, like longest increasing sequence. Like the
Mhm.
classic problems, like everyone should know. So we ended up doing 30 problems in this lightning round. Um,
Right.
but it was really fun to watch the scoreboard. It was
Yeah.
surprising, like as a coach. So I think there's something to what you're saying, because the score was just going up so fast that every few moments somebody was solving something. So I think
Yeah.
like having a few more of these lightning rounds, like maybe something like 2 hour contest, 20 problems.
Mhm.
So maybe they're not trivial, but maybe they're like, maybe the code isn't very long.
Yep.
Maybe the description isn't very long. I think that'd be really fun to watch and it'd be fun to do a broadcast on. Uh,
Mhm. We actually had something similar. So there was a contest before called Open Bracket Delaware, and it was a live contest. It was for U.S. participants only. But they tried something out where the final round was 6 different problems in 35 minutes, and your goal was to obviously to get as many of them as possible.
cool. I think
And it
that's,
was really, yeah, like it was really fast paced and fun.
yeah, well, I like the 35-minute contest idea because you can watch a match in one sitting.
Yeah.
So, like, when you think about like video game contests, that's I don't know. You watch a lot of like I guess Twitch streaming of like video game contests or video
Mhm.
game competitions.
Yeah. Yeah. Exactly.
Which games do you watch?
I watched a few different games. My big one personally is Smash Melee.
Okay,
But
so
yeah, I definitely agree. It's kind of like the length of the a tournament set is what they call it. It's usually order of 15 minutes. And yeah, it's the kind of thing that you can watch in one sitting, and it's the kind of thing where you get to see the ups and downs, right? Like you get to see, um, if someone makes a comeback, you get to see somebody's emotions if they get unlucky or if they mess up or make a mistake or something like that. And I think that we have a lot of the same thing. We like you said, if we show their streams, if we show the webcam and so on, like you'll see a lot of those same reactions basically, and you'll get to watch that. And I think there's a lot of potential to make something really fun there.
yeah,
Yeah.
yeah. So this is actually kind of similar to me. I've been watching and playing a lot of the game Hearthstone.
Okay.
And it's not really to play the game. I'm actually doing some research involving the game Hearthstone.
Uh-huh.
But maybe I'll talk about this on stream at some point once that research is published and then can talk about it. Um, but I've been looking at a lot of these streamers for this game and how they provide commentary when they're thinking about the game and trying to get ideas for either algorithms live like my own channel or thinking about these broadcasts because I've looked at a few of the rounds that they've given and like seeing how commentary differs for like a Hearthstone tournament versus like a ICPC or TCO tournament. I think
Mhm.
there's a I think you're right. There's a lot of room to draw for these video game tournaments, and see how they make it exciting for contestants that we could use in competitive programming. So,
Yeah. Yeah, exactly. I've also watched a lot of chess streams. So we just had a couple
cool, cool.
the chess championship, right? Carlsen versus Caruana. And that one I think is actually also pretty close parallel, I would say, to our traditional competitive programming contest now, right? Because it's kind of like a single game goes over the course of a few hours.
Hmm.
There's a lot of kind of like, you're not making moves every second or anything. You'll see kind of like pauses of 10 or 15 minutes between moves.
Yeah.
And I thought the commentators there did a really good job too, and a lot of that came down to the play-by-play, just talking about like what do we see in this position, what could come out of it, but also what is Carlson thinking, how is he feeling,
Hmm.
what is Caruana thinking, and they were able to really make that into something interesting. So yeah,
Yeah, I play. So one game I love playing is Go, just because I feel like the rules are really simple and the strategy is really hard. And
yeah,
I used to play chess, but I've just found there's something like aesthetically pleasing about Go, so I like playing it.
yeah,
But it's kind of the same thing you're saying with chess is the broadcast for a Go tournament. Um, you can like think about okay, you basically have an expert on your panel that can like analyze the game and say, okay, I think this is what they're trying to do here, or one thing I think they do really well at is a lot of your viewers aren't at the like master level,
yeah,
right?
yeah,
And
absolutely.
you kind of have to communicate what's going on to someone that's like at an amateur level or like at a slightly lower level with the the competition. So I think that was one thing that I applaud you on for the TCO broadcast. I think you did a good job of like explaining things in a way that would be accessible to someone kind of in the middle tier of competitive programming. Like
Mhm.
so maybe like lower ranked Div 1 could really understand what was going on, and
Yeah,
get a lot out of the problem.
mhm. Yeah, yeah, for sure. I think it's yeah. I mean, it's always kind of a tough question, right? Because at any kind of these games or competitions, there's going to be a wide range of skill. And I've definitely seen that the best commentators, at these like chess or Smash or whatever, like are really able to make it exciting and interesting for all levels. And that's something that I personally aspire to as well. So
Pretty cool. Are you going to be doing more commentating outside TCO?
we'll see. I hope so. I might. So I'm most likely gonna be in Porto for ICPC this year. I think we just talked about that. But hoping to, if not the official commentary, to do something there and kind of to do a stream or something for the community. So I think that'd be fun.
Yeah, cool. I actually that's one area we can move into. Did you ever watch Piotr and then Endigorian and Taurus stream?
Yeah,
They did one for ICPC the last 2 years. I think it was pretty
yeah,
good.
yeah, yeah. And then they do the problems side by side and make all the contestants look silly. Yeah. No, I love those streams, and it's a lot of fun too. I think obviously their stream is a lot more focused on, really getting into the depths with the problems.
Hmm.
But yeah, I mean they do a really good job of it, and obviously they're also very very good competitive programmers, so that turns out well.
Yeah, yeah, pretty cool. I want to see more of these kind of streams. I think they're really fun. It's tough on an online competition. So in an ICPC environment, right, you have the competitors, they're completely cut off from the internet. There's no way to cheat. But for
Mhm.
a live like online round,
Yeah,
that's one of the things like you can't stream the contest as it's going on.
yeah, exactly.
Yeah,
Um,
so can you think of any way around that, or can you think of a way to like have a
right.
live stream during a contest that would work?
Yeah, so what we did, for a few rounds with Codeforces is we would just do kind of a post-round stream. Some things worked out nicely there, right? Where, obviously after every contest, most of the contestants are thinking, kind of trying to figure out how to solve the problems that they didn't get, trying to hear about that. Also, obviously, waiting for the results. And so, in some ways, the slow system tests on Codeforces actually were a huge benefit for us because people could watch our stream while they were waiting for that. So that was kind of one way to resolve that. Is to just do it after the contest and do more of like an analysis mode instead of a live mirror. Um,
Yeah, I think that's pretty
I
cool.
like
I
that
remember
one.
maybe this was before your time in ICPC, but for North American contests, we used to have joint practices, and then we
Mhm.
would have a live Google Hangout where we'd all discuss the problems after the contest.
I remember that. Yeah.
Yeah,
Yeah.
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 Oh, okay. So you're actually involved in that. I think that is a really cool idea. Maybe I should try doing an Algorithms Live episode in that style. Grab some guests we can talk through around after. I think that would be really fun. So you were doing that on Twitch, is that right? Or
Which that's right. Yeah.
yeah, who were you doing the reviews with? Because I completely missed those. Is the interesting part.
Yeah, yeah, you should check them out. So some of them I was doing with Stephen Howe. He goes
Okay,
on, who goes by Stephen K Plus on Codeforces. And then
is
some of them
this
I
how
was.
you spell his name?
That's right. Yeah.
Yeah.
Then the some of them I was also doing with Andrew, who goes by Eknerwala. Obviously, both really really fantastic contestants, and we all live, in San Francisco together. So
Yeah, yeah. And they were members of the MIT team, or were they on your team at
they were
Harvard?
on
Or?
the team the same year that I was on the Harvard team. So that was back in 2016, and now we're all in the Bay. Yeah, and it's always fun. I mean, definitely a lot easier to do with multiple people. I think. I've seen some of your streams with just one person where you really make it work. I've seen some of Ericto's as well. I think for me, it's like I really, really like having someone else to kind of bounce ideas off of, and it definitely helps that way. So,
Yeah. Well, I think that was so. There's obviously like a lot of inspiration for doing like algorithms live. One of them was after like in my experience with ICPC, a lot of the training we had a pretty large group at UCF, and we'd
mhm.
talk after the contest amongst ourselves about the problems. And I felt like that was missing from a standard problem review, and be something kind of cool to capture is like that conversation after a round, where you
Yeah,
talk about problems one on one, or if I'm teaching someone something, they end up asking really good questions that I wouldn't think to talk about. And so that was something I definitely wanted to cover with this series. So yeah, I definitely want to have more guests where I can get some advice on like how to improve the streaming. I obviously the Arichta episode was or is it Aricto? I keep pronouncing his
I
name.
honestly I don't know. And I
He
know his.
corrected me and I completely
Yeah.
forgot which way to pronounce it, but it's kind of
Whenever I
interesting.
get too nervous about it, I usually just call him Camille. That's his
Camille.
real first name. But
Yeah, yeah.
yeah.
That's yeah, I was just calling him Camille during the episode because I realized I completely like when I introduced him, I gave
Yeah.
him by his handle and I completely pronounced it wrong and he corrected me. And now I
Uh,
can't remember which way is the correct way to pronounce it. It's really
how do
hard.
you pronounce your handle, by the way? I've been wondering.
Oh yeah, yeah, yeah. So mine's Takin. So, but
Okay.
I don't mind if people say Tekken either because both
I
are
was
kind of.
wondering if you're like, a fighting game player, like the
Oh
game.
yeah, yeah.
Is-
There's kind of a history there with the fighting game Tekken, but I've never played that game.
I see.
So I take that back. I got this handle in high school when I was playing some video games, and I had never played Tekken before. And at some
Uh-huh.
point, we ended up going to a pizza place that had a arcade that had one of the games in it, and that was my first time playing it. So, yeah,
Okay.
I did enjoy as far as fighting games are. I did enjoy Dead or Alive series more, but yeah, I it's been a long time. I used to be the main game I used to play competitively or like play pretty seriously. Just going back to the games conversation, I used to play competitively Ninja Gaiden. Uh,
Okay.
and what's interesting about that is there was this tournament in Japan called the Master Ninja Tournament. And there was a guy that competed in the finals. He got second place and he was from Canada. And this was his handle. And you may recognize this handle from Topcoder or Codeforces or any of these things because it's the same person. This is Derek Kissman. He's
Really?
a world finals judge, right? And
Yeah.
he's also one of the best, or at the time was one of the best Ninja Gaiden players.
I
So
never knew that. Wow.
yeah, so it's really funny because I'm still friends with a lot of this like Ninja Gaiden community, And he's also like he's known for doing speed runs for various other games. So used to, yeah. So it's really interesting when you look at the gaming community and you look at the competitive programming community. There's actually some overlap. Um,
Yeah.
and I don't know. I should probably have more conversations with people because I don't know like who's in what community and like which games versus competitive programming. But I think
There's so much intersection too with all these different communities. Like I know someone who was a professional poker player and then switched to competitive programming
yeah,
after.
there's it's
Or yeah.
interesting too. Think about professional poker players because I in high school there was Sam Soverall, I think his name is, and he went to my high school. He was really involved in competitive chess, and now he's like a world champion poker player or something like this.
Oh wow.
So there's like the connection between like Go community, chess community, competitive gaming community, and competitive programming.
Yeah.
I think maybe it doesn't get highlighted. People don't talk about these other interests that they have. But I think it's really interesting. I should always like maybe ask my guests, oh, do you do anything else competitively? Because I think that's interesting. Have you? Well, let's start there. Have you done any other competitive games that?
Yeah, I mean, I play Smash in tournaments. Other than that, I haven't done anything too crazy. I mean, I used to spend a lot of time on poker. Not anywhere where I was seriously considering going professional, but I played like well enough to beat the casinos and things like that, and to play online profitably. Um, so those are a couple of my interests. Yeah.
Yeah, pretty cool, pretty cool. Oh, so that was an interesting little segue in the conversation.
Yeah.
I think what we should do now is venture back to Venture Cup.
Uh,
Uh, I didn't mean to do that, but I'll take it. So, uh, tell me a little bit about like how Venture Cup started and its role in competitive programming. I'd say.
Absolutely. So I guess kind of a little bit back to my story. So after I was kind of wrapping up with like seriously training for competitive programming, obviously I still do it for fun. At that point, it was around like 2014, 2015, and I worked at this company called Adapar,
Hmm.
which is like a financial analytics company that was funded by a venture capital firm called 8VC.
Hmm.
So I got to know a lot of the people there and got to work with the people there. And VCs are always, always, always looking for talent for their
Hmm.
portfolio companies. Any tech company is always looking to hire. That's just kind of the state of the industry right now, is that there's definitely not enough, software engineers, software developers. And so one of the ideas that I pitched for them is that we run a contest on Codeforces to find people who are interested and to potentially recruit people. And so that's what started the ABC Venture Cup.
Hmm.
And I believe we first ran that in 2016. And so that was a lot of fun. Had a really good turnout too. We had thousands of people who competed in the contest. We had quite a few people who applied and came through the system as a result, and a lot of them ended up getting hired by these portfolio companies.
So, can you tell me like what the interest in VCs are that VCs have in competitive programmers in particular versus like normal software engineers?
Yeah, definitely. I have a lot of strong, feelings about this particular topic. Personally, I think that, you know, I think that there's a lot of carryover. Basically, I think there's a lot of things that you learn as a competitive programmer that are really applicable to software, if not the algorithms themselves. A lot around debugging, learning to understand code, learning to produce code quickly, to understand the trade-offs, to deal with time and memory and all of the complexity and all of that. And even to just kind of approach problems and break down problems is really, really helpful.
Hmm.
And so any real source of kind of new talent really is huge for VCs, for tech companies as a whole. Google, Facebook, anything, startups, venture capital firms. And so I think more and more kind of different companies in Silicon Valley or out of Silicon Valley have been taking this approach of really tapping into the contest community, and a lot of the companies that have honestly have been doing really well. So
So, For people that aren't familiar with venture capital, what is venture capital's role in tech companies, and like what is it exactly?
Yeah, absolutely. So what a venture capital firm does is essentially they go around the world and talk to all these different startups who come to them and ask for funding. And so they're very, very choosy and they're very selective. But once they do decide on who they want to fund, they give them cash flow in exchange for equity in the company. So they have a percent ownership going forward. And they also do whatever they can going forward to try to help those companies succeed. So those companies are called their portfolio companies.
Hmm.
And sometimes, helping out with the portfolio companies involves giving strategic advice about, for example, what industries they should target or so on. But a lot of the time it actually comes down to hiring, to just finding the right people, making connections for them that these portfolio companies need. And so that's a lot of what the VCs do as well.
How has this relationship you've had with VC helped you with your own startup endeavors?
Oh, it's great. Yeah. I mean, so they are one of the angel investors in our company, and they've helped us connect with other good investors, potential people. And yeah, I mean, honestly, it's fantastic. It's part of the whole kind of, Silicon Valley, just kind of the whole industry and how all that works. I'm sure we could devote, many, many episodes talking about just that as well. But yeah, and I mean, it's an interesting industry, but I would say that for the most part, kind of the incentives are set up well, and it's kind of like everyone really is kind of backing success and trying to get things to the point where they can succeed. So
So, who are some other people in the competitive programming community that are involved in venture capital?
yeah, a lot of people. Honestly, it's really cool to see just kind of 5 years out, 10 years out, 15 years out how all these competitive programming people do. So, in the startup world in particular, Adam D'Angelo is famous. He was a silver medalist at IOI, I believe, in the year 2000, and he was the CTO at Facebook and is now the founder of Quora. So he's doing fantastically well. He does a lot of angel investing himself. A lot of other, founders, early startup employees, employees at Google or Facebook, or people who started their own companies that did really well. A lot of these came out of competitive programming founders. So
Cool. Yeah, Dion's doing quite well too. He
yeah,
was,
Dion is also doing great. Yeah,
yeah,
yeah.
yeah. Dion,
He's hiring new competitive programmers too.
yeah,
So.
he started. I had him on in my first episode, and he was telling us a little bit about his current startup, and then he moved to a different startup with one of his friends, and they were doing quite well. And he's also a world finals judge now, so he's like between like everything that he's doing in his life, it's pretty crazy.
Yeah, he's making it work. He's doing really, really well. So
Yeah.
yeah, and he's a great singer. You should see him at karaoke night if
Oh
you have.
yeah, yeah. We talked about that briefly. We were gonna when I was out in California, we were going to go karaoke. That's also something I love to do. So it's something like Dion and I have a lot in common. And yeah,
That's really, really cool.
yeah,
Yeah.
we both want to go out and do that sometime. But we didn't quite make it work. He's been pretty busy.
Uh,
But obviously, if you're starting your own company, it's going to
it's
require pretty
a
much the
lot.
dedication that you require like early competitive programming if you want to get to a really high level. Like you're basically
Yeah.
just always thinking about it, always working on it. So
Yeah, exactly. And there's so many different things you have to tackle too, right? There's fundraising, obviously. There's making all these product decisions, marketing decisions, strategic decisions, recruiting, hiring, technical work, and it's like, yeah, there's so many different things that you have to balance, and so many different things that you have to do well. Um, and with a small team too. So yeah, it's a very yeah, it's tough.
so what would you say are skills that you don't learn from competitive programming that you should probably like develop in yourself if you want to be successful in this area?
Interesting. Yeah, that's a really good question. I would say so my competitive programming experiences was predominantly from IOI, right? And ICPC kind of came afterwards. And IOI obviously is mostly an individual contest, so this may be affecting kind of my view on this. But I think a lot of what you don't learn is essentially the side of working with different people. And that comes through in a lot of different ways. Whether it's just like being able to explain engineering topics well, or being able to just kind of like handle the team aspect, settle conflicts, settle these decisions. And obviously, that's something that you can learn over time. But I do think that that's kind of one of the first things that a lot of these top competitive programmers find themselves kind of having to learn when they come in.
Hmm. Yeah, I definitely agree with that. I think the one thing that can help with the explanations too is if you're teaching younger students, that's like maybe it looks like, okay, I'm not improving myself for contests or something like this, but I think it's something that really helps you in the long run, especially like outside ICPC, outside competitive programming. But even inside competitive programming, I think you just understand topics better. So that's a really important point.
Yeah, 100% agree. Yeah, it really makes sure that you understand the topic, not just well enough to use it, but also to be able to explain it simply and to go through the steps, which is not easy. Yeah. So.
Yeah, and also being able to explain something to a non-technical person.
Oh yeah, yeah, yeah.
I think that's something that maybe is undervalued, but I think is really important. So try explaining competitive programming to somebody who's never done competitive programming before. Try to come up with like a 5 minute pitch, like saying like what competitive programming is. I think that's kind of a fun exercise if you want to practice that skill. Uh,
Yeah, yeah.
I think I talked to Brian Dean. So Brian Dean's the USACO director, and maybe I'll talk to him about this more in the future. But he always says like the skill that you should develop that is like you don't learn in competitive programming or maybe even like in a computer science degree is like the ability to write well,
Mhm.
because his view is like you're going to do more writing than you think, even if you're like in a tech
Yeah,
job or whatever you do after programming contests, whether it's research or a tech job or something entirely different. Um,
yeah, definitely. And I think too, it's kind of like the community that we have, we have a bit of a bias, I'd say, just for kind of like really hard, concrete truths, right? We love math, we love logical proofs and so on. And so much of writing and communication in general is all about these kind of like soft explanations or these soft concepts and ideas. And I think that's one reason why kind of people initially, I would say from the community, people initially, shy a little away from it. Um, but yeah, I mean, there's so much there, and totally agree. It's so whatever you do, it's going to be so impactful. So.
so how did you develop soft skills within yourself? Because you obviously need them to be a CTO of a tech company.
Mhm.
So what did you think you did during college or high school that helped prepare you for that side?
That's a really interesting question. I think, yeah, so teaching, like you mentioned, I think is fantastic. Also just kind of learning to not really be shy and to go out there and to, even to just be okay with kind of messing up or making mistakes the first few times. That's always hard when you're getting into something new. But, practice, will make you better. And I personally still think I have a long way to go. But, yeah.
So did you do any clubs or did you do any like extracurricular activities that you think developed your soft skills or?
Let me think. Yeah, nothing too crazy. I mean, I think I guess I wouldn't call it extracurriculars necessarily, but yeah, I mean, I would always kind of try to push out of my comfort zone a little bit and kind of to just put myself in situations that I wasn't super comfortable with.
Hmm.
Kind of to go for the best learning opportunity instead of the most comfortable option. And yeah, I think I got a lot of mileage out of that personally.
Okay, so let's move into talking about this problem group projects, which was from Venture Cup. Was it this year or your first Venture Cup or?
In 2016, that's right.
Okay, so it was from DC 2016.
Yep.
You can see this on Codeforces.
Yep, let's do it. So just to go over the problem quickly. So we have n different students. n is up to 200. Each student has kind of speed that they work at. So they have a number of minutes A of I, which is their personal number of minutes to finish their piece of a project. And what we want to do is we want to partition these students into groups. And so we can do any number of groups. We could put them all in one group, or we could put everybody in their own individual group. The groups can be any size. The question is, we want to measure for any, let's say a partition that we have, we'll call the imbalance of that partition the sum for each group of the slowest person's time minus the fastest person's time. So we'll call that the imbalance of a partition. And the question is just that we want to count the number of partitions that have a certain maximum imbalance K. Some more constraints on the problem. Each of the AIs are up to 500, and then the K, the maximum imbalance that we're looking for, is up to 1,000.
Yeah. So my first question to you is, can the groups have to have at least one person in them, right?
Yep, each group needs to have at least one person.
Okay, cool. So pretty simple problem statement. I notice a lot of writers like doing this is just having like a really simple problem and then let the structure of the problem naturally make something more complex.
Yep, yeah, exactly. I think there's a lot of beauty from like starting with something simple and building something complex out of it. Yeah.
Yeah. So was there an outside inspiration to this problem or?
Nothing crazy. There are a couple ideas, basically. I think this is kind of one of these kinds of problems where I would say it went in reverse order. So the final DP idea, basically, we had and we were working with, and we built a problem out of it that kind of really highlighted and showed off this idea. And we were thinking, in retrospect, what kind of situation or what kind of story would make sense, for those constraints, and that's how we got to this.
So you started with like the DP idea before you even had a problem, or?
Yeah, exactly. Or like we had like kind of like mathematical constraints basically that led to a really interesting DP solution.
Okay, cool. So let's walk through just like an example of one such partition so people can understand the problem.
Yep, absolutely.
So just give me some numbers and.
Yeah, so I'll just give you the first sample, which is there are 3 students, so n is 3, and their AIs are 2, 4, and 5, respectively. And the K, which is the max imbalance, K is 2. Right, so again, the question is just, how do we partition these 3 students into any number of groups? How many ways are there to do that, such that the sum of all those imbalances is 2, at most 2? So obviously, one way that we can do, which will always work for any n and for any k, is we can just put them all in their separate groups, right? So 1 for 2, 1 for 4, and 1 for 5. In this case, each group's imbalance is 0, right? 2 minus 2, 4 minus 4, 5 minus 5, and so the total is also 0. And that's always going to be, small enough to fit in. So that's one way to do it. Another way that we can do it is we can put the 4 and the 5 together in one group and then make the 2 its own separate group.
Okay.
So yeah, go ahead.
Oh yeah, I had a question. Is this number 2 and then 4, 5 the same count as the same as 4, 5 and then 2?
Yeah. So the way we count a partition is basically it's just the set of groups. So if 2
okay.
are together in a group in one setup and they're not together in a group in one other setup, that means it's different. Otherwise, it's the same. So 4, 5, and 2 and 4, 5 are the same. Basically, we only count them as one. Yeah.
Yeah. So we don't have to count this. Yeah, I guess you can create like a representative of each group, and then you could give like an ordering.
Yeah, give an ordering, and the smallest one is the representative, something like that. Yeah, yeah. And then the last configuration that works is to put 2 and 4 together, and make the 5 its own separate group. So you could see any configuration where the 2 and 5 are together, right? Then that imbalance will be at least 5 minus 2, which is 3. So that won't be good enough. And so basically, these are the 3 configurations that turn out to work. So the answer is and yeah, one quick thing I want to mention is the answer can be really large. So we're just asking for its modulo 10 to the 9 plus 7 to keep things simple. The first idea, obviously, is to just do what it says on the tin, right? To go through all the partitions, figure out the imbalance of each one, and then decide whether it's good enough, right? So maybe we can talk about how exactly that algorithm would work or what it would look like.
Oh yeah, we can talk about that. So you're thinking some kind of like brute force solution where we just go over all the partitions. So we're trying to come up with like a brute force partition kind of algorithm.
Yep, exactly. Yeah. So let's say n was super small, it's like 8 or something, which gives us enough time to just loop over all the possible partitions. And the question is just how would we write that basically? How would we write some code to loop over all possible configurations?
Okay, cool.
So I think your idea, that you just mentioned of kind of just like indexing each little subgroup by its earliest element makes a
Mm.
lot of sense to me. So let's start with that, right? So the first, in this particular example, it's 2, 4.
Yeah, so if this was one group, we could say that 2 was the representative of that group.
Yep. Yeah, exactly. So let's say we're trying to find the partitions of this group, the 2, 4, 8, 9, right? So obviously the 2 is going to be in some group. Like let's just start with the 2 and think about what group is the 2 in. For each other element, the 4, the 8, and the 9, it can either be in the group or not be in the group, right?
Mm-hmm.
And so in that sense, we kind of have 2 to the power of n minus 1 possibilities for what are the groups that could contain the 2. And again, some of those examples, it could be just the 2, it could be all the elements, 2, 4, 8, 9, maybe it's 2, the 4, and the 9, maybe it's just the 2 and the 9 or whatever, right? But there's all these different possibilities, right?
Well, I guess we want to fix the 2, but you could kind of think of it as like a mask
Yeah,
and
yeah.
binary and just, yep. So, all right, so then you kind of think of it a little bit like dynamic programming, but then just instead of encoding the state, you do a kind of brute force. So you keep track of like a mask of what you've taken so far, and
Yep.
then you always
So
just put the earliest element in the group, like force it to be in the next group.
yeah, exactly. So you're already a couple steps ahead of me. But yeah, exactly. So at each point we're just thinking, looping over all the possibilities for what could be in this group, and then we have a recursive algorithm that solves the rest of the group being split into a partition itself, and go from there. So that'll work. It's a bit tricky to think about the runtime because that kind of that begs the question: what is the number of partitions? But in general, it's pretty large. It's on the order of about n to the n to the power of n
Hmm.
is a really, really simple argument. If you just think about, because there's up to n different groups, right? And you can assign each of the n elements to one of those n groups. In practice, the number is a little bit smaller than that, but it's kind of that general idea, basically.
Okay. Yeah, it was like the first thing I was thinking about is maybe it was like subsets of subsets or something like that, but I guess it's not quite that general. Could you do this in 3 to the n? Like subsets of subsets is 3 to the n. Is
Yep.
there a way to simplify this brute force to get it down to 3 to the n?
Yeah, absolutely. So I think you're already a little bit ahead of me, but yeah. but
Yeah.
but I guess to wrap up the brute force to end to the end, once you have all your groups at the end of the recursion, then there's no one left that needs to be assigned. We just add up the max minus the min of each one, and if it's less than k or less than or equal to k, then we add 1 to the answer, and if not, then we just keep moving, right? So the 3 to the n solution kind of uses a pretty common dynamic programming trick to take advantage of this state as far as where we're at, where some of the elements have been taken, some of them aren't. Presumably, we also have some total score so far.
Mm-hmm.
Um,
So
yeah.
let's write out the state, maybe just like the method signature. So it's like which element we're currently considering taking.
Mhm.
Is that right? And then we basically have a mask of which ones have been taken so far, which ones haven't been taken.
Yep. Yeah. So if you want to be kind of, you can combine these two into one, right? Where the mask also inherently tells you which one is the
Right.
next one considering, right? Because it's the first one left.
Yeah, so
But
this isn't adding anything to our state, but if we were coding it recursively, we might want to include this anyway, just for convenience.
sure.
Yeah, yeah. Okay, cool. So
And
really,
the I in the mask, and then there's actually one more that we need, which is our current sum of imbalances.
why is it sum of imbalances?
It's the current total imbalances of the people that we've seen so far.
Oh, so it's your current group. Okay, so let's write this out. Are we sorting these elements beforehand, or are we just going through in the order that we've
We can
been?
just go through in the order. Obviously, it never hurts to sort, but yeah, I mean, it works in the original order as well. So basically, the first one bit in the mask is going to be our I, right? And the question that we're trying to answer with this function is essentially the we've assigned all of these elements so far. We have this set of elements left that we still need to assign. How many different ways are there to assign the rest of the elements so that the total sum of imbalances doesn't go above k?
Ah, okay. So this was something I misunderstood in the problem. I thought that the like your maximum imbalance could be at most k and not the sum of the
Oh
imbalances.
yeah, it's the sum of the imbalances. Yeah.
All right, all right. So if you had something like 2, 4, and then you had something like 8, 9, and then you had something like 10, 16,
Mm-hmm.
and then so this is imbalance of 2, and then 1, and then 6, then you add these together, and that's the number that has to be less than or equal to k.
Yeah, and your total is 9, exactly. Yeah.
Okay, cool. So I completely missed that on the explanation. So
Yeah.
maybe somebody watching will also have made the same mistake and want to clear this up. Okay,
Yeah, no worries.
so this
Um,
makes sense that this is part of your state. So it's the sum of all the imbalances that you've seen in the previous groups, and
yeah.
then somewhere in here, there's kind of a pretty cool subsets of subsets trick for DP sum. Do you remember the formula for that off the top of your head?
So I'm actually not sure I know this trick, but usually what I do is I take the set of bits and then I enumerate over the 2 to the n subsets of those bits.
Huh. Yeah, yeah. But there's a way you can code it kind of conveniently. Let
I
let
think I know
me.
what you're talking about. Yeah, it's like it uses kind of the choose complement trick with negative numbers and stuff to figure out what the next bit is that you can increment or something like that.
Yeah, yeah. I actually have the code. Let me pull that up real quick.
All right. Yeah, yeah. So it's a little like choose complement trick. Basically, SS minus 1 puts it takes the lowest indexed 1 in the binary and turns it to 0, and turns everything after that into 1s. And then you do the ampersand with set. In this case, set is mask, right?
Yeah, yeah. So the set is the mask of what you have left to take.
Yeah.
So it might be like you flip all the bits in mask with the bits that you had left to take, and that's what you would get for set.
Mhm.
So there's probably like if you had we could do something like this where n is a number of elements and then subtract 1 from that, and then you could subtract mask, and that's going to go to set.
Right.
So that's like the set you have left to take, and then you can do all subsets of what's remaining, and that ends up being this mask. So it's pretty handy. There's a couple of things you can note about this though too. Is I kept saying this was like a 3 to the n trick, and it looks like okay, you have like 2 to the n options for mask, and you also have like 2 to the n options for like the subset of subsets. And then
Right.
I
But
said,
it has to be 3 to the
yeah,
n.
and then it's like goes down to 3 to the n. Do you have a good explanation of why this goes down to 3 to the n and it's not 2 to the n times 2 to the n?
Yep, absolutely. So the reason that it is basically the way you can think of counting this is why. So where does 2 to the n come from in the first place? The reason is each of the n elements can either be on or off, right,
Mm-hmm.
quote unquote. And so that's two options, 2 times 2 times 2, n times, right? In this case, we kind of think like the on has 2 more options and the off has 2 more options, but it's actually not quite that way, right? It's like in some sense, only the off has 2 more options. So the mask is the mask, right?
Mm-hmm.
And what I'm trying to get at is each bit here, each of the n elements actually has only 3 options, right? It's in the mask itself,
Right.
not in the mask, but it is in our current subset, and it's not in the mask, but it's not in our current subset. And so those are really the only 3 options, and that's why that turns out to be 3 to the n. So yeah, some pretty neat combinatorial arguments. If you go through the algebra there, you'll also find out that the binomial theorem works out.
Yeah, yeah, you can do that. What I like about this subsets of subsets trick is there's a way. If you look at the binomial theorem, there's a way you can rework the binomial theorem to show that it's 3 to the n. But I
Yeah.
always like this combinatorial argument where it's like, okay, 2, it's definitely in mask already. 1, it's not in the mask, but it's in subset. and then 0 is like it's not in anything. And there's
Yeah,
no way you can have any of these options. The one that's missing is it was in mask, but it's not in the subset. And
yeah,
you
exactly.
you would never have that case.
Right. Right. Yeah, yeah, and I totally agree with you. I'm kind of partial to the idea that any nice like algebraic identity has a combinatorial reason behind it. It's always nice to try to kind of really understand why it is rather than being able to push the numbers. But yeah, so to finish the kind of the DP idea, I think there's something inherent with the Go function that kind of leads to the DP. And basically the idea is that all we really need to know enough information about our state right now is the mask of what bits that we've taken already and our current sum of imbalances, right? We don't need to know how many groups we've made already. We don't need to know what those groups were, who's in what group. As
Hmm.
long as we know who's left and how much imbalance we have left to work with, that's sufficient for the answer, right?
Hmm.
And so, the DP solution basically, there's lots of different ways to do this. Probably the simplest way with what we have written right now is to do some memoization
Hmm.
on this Go function. So if we call the same mask and same sum of imbalances that we've already done previously, we just use the memorized answer instead of having to do the math again. And like you said, so that ends up being 3 to the n times k.
Right, in total runtime, and then the amount of memory we're using is 2 to the n times k.
3 to the n times k. Yeah.
Yeah, so
So
that's memory runtime. Yeah.
yeah. So this one is pretty interesting because I guess before we had an n to the n, right? It had no dependence on k. Now we've added a little bit of dependence on k. We're lucky here in this particular problem that k is pretty small, so that's fine. But the n component has gone down from n to the n to 3 to the n.
Hmm.
Um, and then, in fact, we're actually going to kind of try to want to go even more in that direction and push more towards using the fact that k is small, basically.
Ah, cool, cool. Yeah, because 2 to the n on 200 or 3 to the n on 200 is way too big for
Yes.
what we want to do.
At this point, with the n to the n, like we were saying, we could maybe do up to 8, maybe 10 if we optimize it. 3 to the n times k, at this point, we're able to work with n up to, let's say, 15,
Hmm.
which is obviously much better, but still kind of still far too slow for the full problem, right? So so everything we've talked about up till now is exponential, right? You store kind of this full mask of which elements you have already, which elements you don't have already. And clearly to get to something that's going to be fast enough or that's going to be, efficient enough memory-wise, we're going to need something that is not exponential. And we're kind of going to have to reframe the problem and think about it a little differently. So do you have any ideas on how we might do that?
So when I read this problem, the first thing that came to mind, and so actually, I guess I could talk a little bit about my problem solving process. When I read a problem, I get a lot of ideas, but I don't like those ideas to influence like where I go with the problem solving. So I just write them down and then forget about them.
Yeah.
And so the first thing that came to mind when I saw this problem is like, oh, I need to sort A of I somehow. Because if I sort A of I somehow, maybe I can make some kind of traction in my state, like encode something not so complicated, and then it'll be easier for me to like work with the problem and then go from there. So that was the first idea that came to mind was I like sort these completion times, and then maybe I could do something with like keeping track of either the biggest element of the set or the smallest element of the sets that I formed, so I know what I could take next and yeah, go from
Ah,
there. So that was the first observation I had. I got a little bit further with that idea, but I wasn't sure if it was the right track to go down. So
sure. So first things first, we're going to just sort all the elements. Basically, each student's work time, we can just put that in sorted order. No harm, right? That makes perfect sense.
mm-hmm.
And yeah, so I totally get what you're saying. It's kind of, now that we have it in sorted order, we know that each group's imbalance is just going to be its latest element minus its earliest element, right? And that's actually really useful because it means that we don't have to we have a little bit of a simplified notion of a group, right?
Mm-hmm.
There's two elements at the ends, and again, it might be the same element, right? But then we have some arbitrary number of things in between. Um,
Thinking about it in terms of the state, you've kind of just simplified the state in an interesting way, where it's like instead of storing like the mask of what you've seen so far, you end up taking like the low value and the high value could basically define each group. Um,
Yep.
and although it does cause this slight restriction because now you don't know like what you did and didn't take within this range. So if you had something like 2, 4, 9, something like this, we lose the information on the four.
Right.
But there's probably a trick to get around that, I'm guessing.
Yeah, exactly. And so I think one of the ideas, which this reminds me of, and it's kind of part of what got us thinking in this direction, is like a parentheses sequence, right? Where
Mm.
you have open and closed parens, and it goes on. In this particular case, it's a little bit different from a typical parentheses sequence, right? Because the parentheses don't actually have to open and close in the same order as one another. Um,
So you're thinking of it as maybe there's like different types of parentheses, like maybe
yeah,
there's red and then blue,
yeah,
and they don't have
perfect.
to pair correctly like this. They can pair something like this. Maybe I'll add one more for clarity. Pretty
Yeah,
cool. Yeah.
yeah. But yeah, that's exactly what I had in mind. And so, just to think about how that relates to the actual students itself, right? Imagine if you had 4 different students in a row, you put the first and third student in one group, you put the second and fourth student in another group, and so on. And so the nice thing about this kind of visualization is, first of all, each person is going to be in at most one parenthesis sequence, or in at most one parenthesis. So some elements are actually not going to be in any parentheses at all. Kind of going through
Oh,
the
okay. So you've got
timeline.
like junk in here. Let's
Yeah,
we'll put them in white. So
sure.
we'll put like question marks. So maybe
Perfect.
there's some that aren't being paired up. Okay.
Yep. And the reason that they're not being paired up again is because they're in the middle of some existing group, right? So maybe those ones on the left there are in the red parenthesis sequence. Maybe then they're in the orange sequence, right? Who knows?
But they just have to be contained by the pair of parentheses sequence. You just don't care which one they're in.
Exactly. Yeah. And the reason that doesn't matter, again, is because we're doing high minus low at the end, so all the elements in the middle don't matter. So this is kind of cool, right? Because, yeah, so each element is going to be in either 0 or 1 different parentheses sequence. And the next thing that's actually really nice about this visualization is those question marks, like we just said, it's easy to tell which parentheses they can belong to. It's easy to tell how many different parentheses they can belong to, right?
Hmm.
The reason it is because just look at the question marks on the left. It can either be inside the red,
Hmm.
it could be inside the orange, right? It
Yeah.
can't be inside the blue because that would actually go outside of the range of the blue numbers.
Yeah.
And so essentially each of those elements has 2 options for where it can go. And those 2 options are independent of anything else in the problem. We could change those at will, and it won't change the total imbalance. It won't change anything, right? No matter what we do from the rest on, the total imbalance with this parentheses sequence is going to be the sum of all those right parens minus the sum of all those left parens.
So you can basically just tell so how many sequences you're a part of just by that sum of open parentheses that haven't been closed. I see.
Yeah, yeah,
Yeah.
exactly. And it kind of reminds you, right, of the how to check a parentheses sequence, which is you do the +1 -1 trick. You keep track of how many parentheses you have open that need to be closed, and it's almost the same idea there.
Yeah. So like if I'll just reiterate this here. So we start here. We get one parentheses open, then we have two parentheses open. So then we're in these question marks. Well, there's two groups we can belong to. Then we close this parentheses off, so we have one less group. So this number comes down to one, and so now we know we can be a part of just one parentheses. And then when we see this number again, this number comes back up to two, and then we can know whether to put something in this question mark or not put something in this question mark. Very cool.
Yep. Cool. So we're making a lot of progress. We have a much better visualization of what's really happening with these groups, and now we got to strike while the iron is hot and figure out how to turn this into a working solution. And so this is actually where the very first thing that you said is really important, which is that we're sorting it. It's completely sorted because it means that we get to go in order of the sorted array. right? And you were just saying, keeping track of the parenthesis score, +1, -1, +1, -1. Well, we can do that too, and we can do that as part of the DP state, right?
Yeah,
So,
yeah.
so we're at some element, and we have this many open parens. We have this much total sum accumulated, and we want to find the number of ways to finish it up here.
Yeah, I'll call it open sum. All right, so this is our state. It's where we're at, number of open parentheses minus closed parentheses, of course, and the sum of imbalances.
Mm-hmm. Yeah, perfect. So this is interesting, and so now this seems like this is pretty much all we need. We should do kind of a little bit more kind of like diligence here to make sure this makes sense. So wait, so real quick, what do you mean by open sum? Do you mean by the
I just mean like, let's say these are the parentheses you've placed so far. It's open sum as the number of open parentheses minus number of closed.
Okay, great, perfect. Yeah. So the one thing that I want to point out is sum imbalance is a little bit tricky, right? Because I think the idea that we were going with before is we go through each group, we add the max minus the min of that group. So let's say inside this DP somewhere we decide to close the paren at I, right? So we want to subtract the max, which is going to just be the value at I. We want to add the max and then we want to subtract the min. And now it's a little tricky because we don't want to store them in, right? That's a lot of state.
Yeah, that's a lot to work out.
And so so there is kind of like I'll call it a slower way to do it, where you have a kind of a state of how much min you've accumulated so far. But the nice little trick here, which again is kind of a pretty applicable trick, is we can actually just go subtract the mins at the beginning. Like let's just include that as part of sum imbalance. Do you see what I mean?
So what you're basically saying is we have our number sequence, and we just assume that when we make this a left paren, that it's the entire sequence.
No. So what I mean is whenever we open a left paren, we just subtract that value from the
Oh, okay. So
right?
we're yeah.
The magic of it is that when we add back in, all of a sudden now it's so now it's perfect, right? Because now
so we're basically breaking up this difference, right? Because this is a sum over these differences. That was really bad. Okay, but it's basically a sum over highs and lows, and so we're just like breaking this into two different things. One is the sum over highs. You can put this in parentheses, and then you can break this into the sum over lows, right? Or we can add and then make it negative. Distribute the negative. And so this is just easier to think about. So every time we add an open parenthesis, we're going to subtract out low, the low value of that pair. And then every time we add an open parenthesis, we just add the upper bound. And I've seen this trick a lot. Lewin seems to really like this in his problem writing, I've noticed. It's almost like a pattern. If I see a round is by Lewin, this is like one of the first things I start to think about is, how do I rework the equations that I'm given in the problem? Because it's almost like a calling card of like a Lewin round, and maybe he'll start avoiding it now that I've called him out on it. But basically, you rework the sum. It's almost like a trick in itself. And I've seen so many problems where you can do this and it just simplifies your thinking. So pretty cool.
Yeah, exactly. So this works, and funny enough, actually, as it turns out, we should analyze the math of it all, but it actually turns out to still be a little bit too slow. So we should let's just kind of figure
calculate
out
the runtime. So how big can this number get up to now if we're doing subtracting low and then adding high?
Right, and so that's where the trouble comes in, right? Is we were saying k is up to 1,000, but the thing is that this number actually it doesn't have to be from 0 to 1,000. It could go way negative, and then we can add enough to make it all back, right?
So how big can this number get?
So it can be essentially as low as negative of n times all of the AI, right? And that turns out to be about 100,000 based on the constraints that we have.
So it's almost like 2 times n times the sum of AIs? Because you can
Or
go really negative and positive, or?
two times the sum of the AI. Yeah. I guess I was
Oh,
including the
yeah.
n.
So, okay, yeah, I see. So 2
Yeah.
times the sum of the AI, that's
Yeah, it can be anywhere from negative that to positive that, right? Um,
so it's like 200 times 500 times 2.
which comes out to be around 200,000. Yeah.
Yeah, it's pretty
Um,
big.
and then open sum itself can be up to 200, right? It's up to n.
Yeah, so this is up to, this is O of n. Um, and then this guy is also O of n.
Yep.
Okay, so better than exponential. So a little bit of an improvement, but we still, this is, the time limit's 2 seconds for this problem, so still not good enough.
Right, exactly. And so the state transition is a little bit tricky, but it can be done in OV1, so that's nice. There's the one edge case you need to be careful about is if we have a group that just contains a single element,
Mm-hmm.
it's kind of we should think of it as opening and closing at the same time.
Okay, okay.
But other than that, the state is relatively easy to transfer, right? Basically, like we just said, we already did the minus low in advance. So if we're closing it, we just need to add high. If we're opening something new, we just need to subtract low. If we want to add it to an existing group, we know how many existing groups we can add. This is the question mark thing, right?
Mm-hmm.
If question mark, we just multiply that by open sum because that's the number of options that we have to put it in.
Mm-hmm.
So all of that, pretty simple. Essentially, there's like 3-4 cases, but that's all doable. So right now, our runtime, I would call it n times what we just said, two times the AI. So what that turns out to be is around n cubed times AI, which, like you said, is a little bit too slow, right?
So it's n cubed times AI. Oh, the max value of AI.
Yeah,
Okay, so
and
call
all the
it,
numbers.
I'll call it A.
Yeah. Okay, perfect. Yeah, so n cubed times a little bit too slow. One more optimization is going to take us there. How would you make this faster from here?
Somehow I feel like we're either going to be able to take off a factor of n or a factor of a, and those are
Yep.
kind of like the two branching paths I can think of about which which approach I want to use. So let's take a look at this state and see which one's more likely.
Cool. Yeah. So some imbalance, it does kind of feel like, the subtracting the lows, kind of as we go through them, it was what I'll call kind of a necessary evil, right?
Mm-hmm.
We had to do that so that the state didn't balloon, but in some way it did already get kind of, it did make the state quite a bit bigger, right?
Mm-hmm.
Because we would love to be in a world where some imbalance can only be from 0 to k, because that's only 1,000 choices as opposed to 200,000 choices, which is kind of what we're at now. So what would be some way that we could try to kind of steer towards that world?
Well, I think we know that it's a maximum of k, and that's kind of like putting this upper bound on what's possible. So maybe we could do like k minus this whole sum here. So there was this sum that we were holding on to. So if we somehow manage to do like k minus sum of differences or sum imbalance,
Mm-hmm.
and some way prevent this from going negative, we might be able to uh, basically bound it by 1,000 instead of n by a.
Right. So the upper end we actually can remove. If you think through the math a little bit, kind of with our sum and balance number, we were saying it should be negative sum of AI all the way to positive sum of AI, right? It actually can't go that big as far as the positive side. It can't go more than k, because your total won't decrease from where you're at now. But it can increase a lot, right? If we imagine, imagine if the first 100 were all open parens and the last 100 were all closed parens, right? That's totally possible, and it could totally happen. And right in the middle that we are there, our current sum imbalance that we're calling it is the negative of the sum of all those things. And that's valid. Like, that could end in a real state, right? So what turns out to happen, the best way to make that work, we could try to squeeze constant factor here, but I don't think that the limits will be kind enough to make that work. But what we can do is we can actually rethink the whole sum again. So we're just talking about the sum of the high plus the sum of the negative lows, right? And we're actually going to have to take another little step forward and rethink the entire sum again. So let me put it this way. If we're going back to our list of parentheses and question marks and everything, right? Between any two consecutive numbers, there's kind of a gap, right? So let's say like one of the AIs is 5 and the next one is 7, or 7 and 8, sure.
Okay, and then we just think of it as there's like a gap here.
There's a gap of length 2, right? And,
Mm-hmm.
you know, basically the way that we're going to think about this sum and balance number instead is we're going to sum up for every gap the number of times that gap was crossed by parens times the length of the gap, right? So let's say this gap was crossed by 2 different parentheses sequences. So there are 2 open parens at this point, and those 2 parens will close later. Then this gap is contributing 2 times 2 to the total sum. Do you see where I'm going with this?
Yeah, so let's we're at this gap. Let's like work through some of this. Maybe this is a question mark that we've dropped.
Yeah.
So
Yeah.
these are the pieces that we're considering. And so instead of thinking of it as like a sum of differences, we're looking at it as a sum of deltas between adjacent values. And we know how much this contributes to this sum imbalance by using this open sum number.
Yeah. Yeah. Let's say like the 7 is a blue closed paren, maybe the 8 is a question mark, the 10 is a red closed paren. Just making some stuff up, right? Yeah. So again, from the traditional mindset, the total sum of imbalances, the blue is 7 minus 1 is 6.
Mm-hmm.
The red is 10 minus 2 is 8. So the number that we're looking for is 14. But the idea is, if we look at each of those gaps, like the 5 to 7 gap is a great example. It has a span of 2, and it's covered twice, so it contributes 4, right? The 2 to 5 gap has a span of 3. It's also covered twice. Yeah, that's a really good, yeah.
Yeah.
Good.
So if there's even an overlap of where you're covering, so if we look at the 7-8 gap, it's not spanned by the blue, it's spanned by the red. So
Right.
we'd only consider that once.
1. So 1 times 1. And if we add up all these numbers, the math works out that it should come out to exactly 14. It should come out to the same number because we're just counting the exact same sum, just in a little bit of a different way.
Yeah, so it's almost like you're reworking the sum again, except you're taking these high-low pairs and you're kind of like pairing them together based on like how close they are, is maybe a thing that you're thinking about. So imagine, yeah, that's how I'm thinking about like the reshuffling of the algebra. So we have like the sum of the value of high minus the low, right?
Yeah.
And so
And,
if what I do is I take all the lows and pair them with like the next closest high, then so in this case these two would pair, and then no, that doesn't quite work.
well, so yeah, I guess another way to put it is like, when you say sum of high minus low, um, to think of high minus, and let's just say, for example, that the high is the a sub 5 and low is the a sub 2, if that makes sense. Yeah. So is to kind of untelescope, to unwrap that sum. And so to make that a5 minus a2, instead to write that as a5 minus a4 plus a4 minus a3 plus a3 minus a2. Right? And obviously that turns out to be the same number. But the reason that that helps is because in all these different sums that we're doing, there's only these n minus 1 differences, quote unquote, that we're going to be involving in them, right? So it's how many D1s do we have, how many D2s, how many D3s.
Yeah, so I'm just rewriting them. It's a little easier thinking instead of like pairs of sums. I just think of it as like D4 is the delta from 4 to 5.
Yeah,
D3 is
perfect.
the delta from 3 to 4. And so if I rewrite them that way, you're just writing this difference again as these D4s, D3s, D2s, and then you're just putting a multiplier on how often this number occurs in this huge sum. So
Yeah.
you're breaking the sum into these consecutive deltas, and then you're just using the frequency of those deltas to calculate the answer.
Yeah,
Cool,
and the
cool.
beautiful thing is that the frequency of the delta is actually already part of the state. It's the open sum.
Yeah, so
And
we're abusing that as already being in our state and then using it for the later piece of the calculation. That's really
yeah,
cool. I like that a lot.
yeah, exactly. And so the cool thing, once we've been talking through all this math, right? But once you actually go through and implement it, the implementation is very, very simple. In fact, it's actually simpler than the very first solution that we came up with, which was to go through the partitions. Um, I would say the code for this last solution, happy to share, is actually the shortest out of all the possible codes. You can write out the entire DP state in 10 or 15 lines, basically.
Yeah. I
Uh,
won't I
and
won't put the code in the episode because I want people viewing the episode to try coding it, but you can see like you can already see the state up here, right? It's
yeah,
like I times open sum time or sum in balance. So let's just calculate the runtime.
yeah, yeah.
Yeah,
So
so the
I
transitions,
have 10 options, right?
yeah, so the transitions, there's only four transitions. They're the same four cases that we analyzed down here. But this
Yeah,
new state, we'll know the runtime if we know the size of the state. So I guess this is n squared because this is O of n, this is O of n. But
uh-huh.
this sum of imbalance can now only go up to k.
Yep.
Yeah.
Because now we're only adding, right? That's the beautiful thing is that we don't have to do the subtracting and adding, which lets us kind of temporarily go out of our bounds. Now that we're only adding, it can only be 0 to k. As soon as it goes above, that's done. It's gone. Yeah, so the total number of states is n times k, n squared k. If you take a look at the numbers, that turns out to be about 40 million total, which is um, basically should be comfortable to fit under the limit. Like you mentioned, Matt, each state has around like 4 different transitions that you have to process, but regardless, that's still fine to
Yeah,
work.
and these loops are pretty tight. So that's the other thing to keep in mind. If you're like n squared times k, but then the number of lines of code you have in the like innermost loop is really large, then that's going to be
Yeah,
pretty close to the time limit. But this you could write as a really tight iterative DP. You don't have to do this recursive DP, and it'll probably run a lot faster. So
yeah, and constant factor as well is quite is quite an art. But yeah, I mean, as it is here, like the natural DP array, like all the caching is really good. The lookups are good. It's not like we're doing random accesses essentially. So it kind of flows through very nicely. You also have some kind of inherent divided by two, where, for example, open sum can't be more than I, right?
mhm.
So um, in reality, it's not quite n squared. It's actually n squared over 2. Things like that actually make it work out. And so in practice, I don't think any solutions with this runtime had any trouble making it into the limit. In fact, I think a lot of them made it in, with even a factor of 10 to spare.
Oh wow, nice. Yeah, even in Java, you think, or
Yeah, even in Java, totally fine. And
awesome.
especially kind of the state transition here is the kind of transition where Java isn't going to be too much worse than C++. So,
Awesome.
in fact, I wonder if there's solutions that pass that are in Python.
Yeah,
It's possible.
could be.
But yeah, so that's the problem. And we were talking actually at the very beginning about how it's nice to have a simpler statement and to get into things more complex. And I think it's personally, I really like that. After all the complex things that we got to, the solution itself is actually also simple.
Right. Yeah, that was kind of the experience I've had with my last two guests where like you start with this like really simple stated problem and then there's all this like natural complexity that branches out from that. And then when after you do all this analysis, after you do all this thinking, the code you have to write isn't very long. I think
Yeah.
that's what there's almost like this elegance or beauty to these kind of problems, and you almost think of them as like a gem of a problem. Or um, I've heard like programming contest problems that have these properties. You kind of describe them like fine wine or something. Like
Ah.
I don't know people. I don't know if there are people that are like problem connoisseurs, but maybe they exist. Something like
Yeah.
this, and they just like really love beautiful problems and. Yeah, and I'm glad we were able to celebrate this one by going over it in such detail and just thinking about all the little tricks that you can apply here. And there's nothing, what I like about this problem, there's nothing like really specialized in terms of knowledge. It's just dynamic programming and then thinking about how to rework some summations.
Yeah, absolutely. And so, obviously this was a pretty hard problem. It was the second hardest problem on that particular contest. I want to say around 20 or 30 people solved it in the contest. Maybe a little bit more than that. But a lot of these tactics or these kind of ideas with dynamic programming all absolutely apply.
Mm-hmm.
Um, and so, each one of the kind of the many ideas that we went over could be its own easier problem. And a lot of these are very fundamental ideas that are common to work with. So,
Cool. Well, Scott, thanks for coming on Algorithms Live and sharing this problem with us. And I hope all the viewers enjoy it as much as I did.
yeah, absolutely. Thanks so much for having me.